So, hello students, welcome back, and let me introduce you to my finite element program GEOFEM. This lecture is slightly different from the previous ones. We are not going to do any mathematical work or anything. We are only going to see how we can apply the finite element program for our solutions. And this particular one, GEOFEM, is developed at IIT Madras as part of several students' project works and PhD thesis, and all the constitutive models that are going to discuss, they are implemented here along with number of other options. And till now we have solved some problems, the problem of the truss element and then the soil structure interaction of a combined footing, and I will just demonstrate how we can do this analysis using this program. And what I will do is I will give you the data files so that you do not need to recreate the data, and what you can do is you can modify the properties, material properties like your Young's modulus or the spring stiffness or something, and run the program for getting your results. And so, we are going to look at the same problems that we had solved earlier. See, one is this truss element with the 3 nodes and 3 elements, and the AE by L for each element is 10,000, and it is applied with a 100 kilonewton load at the tip at this point 2 in the x direction. And we had considered 2 cases. One is the left side support on a hinge and the right hand side on a roller, and then we have also considered the case of settlement of this right hand side support by 50 millimeters. And we will see 2 methods for simulating this. One is by exact method and by the boundary spring method. And by the boundary spring method we can even vary the spring stiffness and see what is the effect on the displacements that we get and then the results. And so this is what we had seen in one of the lectures. The right hand side support settles by 50 millimeters, and then the entire structure is just simply rotated, okay? And that is one problem that we are going to consider. Then the other one is the combined footing with supported on soil, and the soil itself is modeled using Winkler springs. Okay, let me show you the finite element equivalent. So here we have this beam, and it is supported by on a series of springs, and this is the loading that we have given. Okay, and so we get different solutions. Okay, and that we will try to see how we can do this in the finite element program. And before that, let me show you this program. And this is the user manual for the program GEOFEM, Geotechnical Finite Element Modeling. It's a simple enough program, and it requires all the finite element analysis. They require a lot of data. We need to define the nodal points and then the different elements, their connectivity, their material properties, and so on. And for doing that, we have to go through systematic procedure for giving this input to the program. And the first line of this data file for any problem is your the title of the analysis, just for your own information: analysis of truss or analysis of truss with settlement or something. Okay, and then the next line is some basic data, number of nodal points, and then the number of element types. Like you may have different types of elements like bar element, beam element, and then a continuum or anything, and depending on the type of elements that you have, you can choose it. And there are totally 5 different types of elements in this program: a bar, beam, and then a nodal link element between 2 points, and then the joint elements, and then the continuum. Okay, 5 types. And then you can consider the gravity forces, and then you can create a post processor file for interpreting your results. And I think I will skip all this because they may not mean much to you. Okay. And then for each node, we need to give the x and y coordinates, and then we have to also tell the program whether it is an active node or a fixed node. And these are the boundary condition codes corresponding to each node. 0 means it is an active node, and 1 means it is deleted, it is a fixed degree of freedom. And then x and y coordinates, and we can actually give the coordinate values either in the Cartesian system or in the polar coordinates, and that we can prescribe by some other input. And the program itself, it has got the bar elements. A bar element is an axial element, and you can define this with the 3 nodes. Actually, I have defined only with the 2 nodes in till now, but later on we will see 3 node bar elements, and these need not be straight, these could be curved for representing say a rope or a cable or something. Then we have beam elements, 2 node beam elements, and these beam elements, they are defined with axial degree of freedom, shear deformation, and then the rotational degree of freedom. And it will ask for moment of inertia I, and if your the beam has a width of b and a depth of d, we need to externally calculate this I as 1/12 BD cube and give that as an input. And then the area, cross sectional area, also b times d, and this particular beam element, it has the shear induced deformations also, okay, and that also needs to be given as an input. So for each beam element, we need to define the node 1 and node 2, and then the material property set number, like you need not have the same material all through. Your length of the beam could be made of different materials, and if you want, you can define. And then the cross sectional area also we need to give, and then the moment of inertia, and then this particular beam element, it can include the shear deformations, but if you do not want to include the shear deformations, we can set that shear area to a very large value, so that we can ignore the shear deformations, and the element becomes a pure flexural member. Then the other type of element that we had seen till now is the spring element. So the spring element is actually, it is a spring between 2 nodal points, and we can define the stiffness, and then we need to define the normal and the tangential directions. And because these nodes, node 1 and node 2 of a spring element, they are having the same coordinates, because basically this is a contact element with a 0 thickness, so there is no separation. And for defining its tangential and normal direction, we have 2 other nodes, node 3 and node 4. Along this line, we have the shear direction, and normal to this is your normal spring direction. And when we use them say for a combined footing, I will explain that we can connect one of these nodes, say node 2 to the beam or to the footing, and node 1 can be your fixed end node that is corresponding to the soil, right. And so let me now open and all the results. Once we run the program, the results can be saved in a text file. Let me just zoom it a little bit. So here this is our results file for the example of the truss that we have done in the class, and there are 3 nodal points, and then there is only one element type because all the elements are only bar elements. Okay, and then the coordinates, x coordinate of node 1 is 0 0, and I have made all the equations are active so that we can apply the boundary conditions and then see how the boundary forces are developing. And then node 3 is at a distance of 5 in the x direction and the y is 0, and node 2 is x is 2.5 and y is 4.3301 as we had seen in the lecture, and there is no rotational degree of freedom for the bar elements. So, this is made as this is 0, okay. And then I have given the Young's modulus of 50,000 and then the area of the element as 1, so that your AE by L, see the length of each of these elements is 5. So, AE by L is 10,000, that is what we used in the class, okay. So, I am giving the Young's modulus as 50,000 and the area of the element as 1 and the length is 5 units. So, AE by L is 10,000. So, we have 3 elements. Element 1 is connected between node 1 and node 2, and element 2 is connected between nodes 2 and 3, and element 3 is connected between 1 and 3. That is what we had seen here. Okay, let me just go back. So, this is node 1 at 0 0, node 2 at 2.5 and 4.33, and node 3 is at distance of 5 and 0, x is 5 and y is 0, and element 1 is between nodes 1 and 2, element 2 is between 2 and 3, element 3 is between 1 and 3, right. Then we have applied a load of 100 kilonewtons at node 2 in direction 1. So, we can apply the load in different directions. Direction 1 refers to x, direction 2 is refers to y, and L code 3 means rotational or moment. Okay. Then actually this particular one is corresponding to settlement of 50 millimeters at the right hand side support. Okay. And these are the results that we get. See, these are the displacements. At node 1 the displacement x and y are 0 because these are this is a fixed end node, and node 2 it has deformed by this much in the x direction 0.065 and y direction minus 0.0264, and node 3 it has moved in the horizontal direction by 0.005 and the settlement is 0.05, that is what we imposed. And then these are the forces in the bar elements. Actually the area that is specified is 1. So, whether it is force or stress, it is the same. Okay. So, in element 1 it is a tensile force of 100. See, the sign convention in this program is an elasticity sign convention. Tension is positive, compression is negative. Okay. So, element 1 has a force of 100 kilonewtons and element 2 has a force of minus 100, and element 3 it is it's a tensile force of 50, and actually you might wonder why it is calculating at 2 points. That I will explain later, because these correspond to numerical integration points that we will see. And the reaction forces at node 1 there is a reaction force of minus 100 to compensate for the right hand side force of 100, and then at node 1 in the direction 2 it is minus 86.6, and node 3 it is 86.6. It is basically it's counteracting the applied moment. So actually we are applying a force of 100 here, and the reaction force, as we have seen, it is basically 100 times 4.33 by 100 times 5 is your external moment, and the couple is the reaction force multiplied by 4.33. Okay. So you can easily calculate the moment, and that is what we get here. So the reaction forces are 86.6 acting up on the right hand side and 86.6 acting down in the left hand side. So if you look at let's see the data file. So this is the data file for this problem of the truss element. So this is actually all the results are stored in a binary file for our post processing, and there is one file name given here, truss.bin. Then as the program is running, we can save all the intermediate data in some files, and this is required. So if you want to stop the program after some time and then rerun, we can do this, because most of these finite element programs, they can run for a long time, for sometimes 2 to 3 days. And if you want to see how the progress is going on, like you can stop after say 5-6 hours, look at the results, and then restart. And for restarting, the finite element program has to read some files. So it is going to read from these 2 files, and if you put a star in the name, it will be opened as a temporary file. So you will not be able to restart. If you restart, it will start from the beginning. Okay. And so if you want to restart any analysis, we need to give a name without a star. Okay. And your Young's mod, these are the element coordinates, and then the boundary conditions that we give for the degrees of freedom, and your Young's modulus is 50,000, and then the cross sectional area is 1. Okay. And then the loading is applied at node 2 in direction 1 of 100. Okay. And these are the boundary conditions. At node 1 we have applied a displacement of 0 in the x direction, and at node 1 in the displacement y direction also we have applied 0 displacement, and then in node 3 we have actually applied 0 displacement. Okay. So and running the program is very simple. So you just type, I am going to give you this program GEOFEM, it is a run unit, and it is going to open a DOS window and then ask for the input file. Okay. You can so this is the input data, and then the I am giving dot out for sorting out these files, that is the output file. Okay. Then I just it will go through and then finish the run, and then you can open the file for looking at your results. Where is the truss? Okay. Okay. So this is your results file. So in this particular run that we have done, right hand side support is not allowed to settle down. Okay. And these are the displacements that we got in the class. We have seen at node 1 there are no deformations, and node 2 these are the deformations, and at node 3 there is a roller, so it will deform only in the horizontal direction but not in the vertical direction. And these are your axial forces. Node element 1 has a tensile force of 100, element 2 has a compression force of 100, and element 3 has a tensile force of 50, right? Okay. And so it's actually very simple to run, and when I give you these programs, I'll put some comments. I'll show you how these comments look like, so that it is yeah, I think I don't have a file here, but I will give you on each line you can put some comment so that you know what you are doing. Okay. And now let's look at this program or this analysis of beam and elastic foundation, and this is your so this particular analysis was done with 16 beam elements. Our total length of the footing is 8 meters, and we have taken we have divided that 8 meters into 16 elements, each of 0.5 meters length. So if we look at our x coordinates, x coordinate 1 is at 0 0, second one is at 0.5 and 0, and actually it is the entire beam is along the x axis, so there is no y coordinate. And then in our analysis we have neglected the axial deformations, so there are no equation numbers in the x direction, everything is 0, and there are only displacements in the y direction. Okay. And we have totally 17 nodes along the beam, and all of them they have the rotational degree of freedom, like these beam elements they have axial, shear and rotational degree of freedom, but I have deleted the axial degree of freedom because we are not interested. So the number of degrees of freedom are 17 times 2, that is 34. Okay. And then below this we have the nodes corresponding to the soil, and they are all fixed, they are not allowed to deform, so that our soil has a firm support. And then in between the beam and the soil at the fixed end we are going to provide our spring elements. And the beam elements, so our Young's modulus is 31.622 times 10 to the power of 8 kPa, and the cross sectional area is 0.3, and then the moment of inertia that we had calculated as 2.25 times 10 to the power of minus 3. I think I may not have copied all the data. Oh yeah, here. So our Young's modulus is 31,622.78 MPa, and in kilopascals 31.622 times 10 to the power of 6. Okay. And the moment of inertia is 2.25 times 10 to the power of minus 3. Cross sectional area is 0.3. Okay. And so that is what we have here. 0.3 is the cross sectional area, and 2.25 times 10 to the power of minus 3, and then the Young's modulus, and the shear area is set to a very large value, so that we do not include the shear induced deformations in our calculations. Okay. And then these are the spring elements, and there are two stiffnesses, one is 8750 and then 17,500. See, the two springs at the edge of the footing, they will have a stiffness of 8750. See, the contributing area for the two end springs is only half length of element 1, and element 1 is of length 0.5 and half length is 0.25. So, the spring stiffness for these two end ones is 35,000 times 1 times 0.5 by 2, that is 8750. Then for the intermediate springs it is 17,500, right. So, we define two material properties, one with 8750 and the other with 17,500. Then when we define our spring elements, see, for these two end springs we have material property of 1. That means that it has a stiffness of 8750, and then all the intermediate ones are linked with second material that has 17,500. Okay. And then there are three applied loads, 300, 600 and 300 at different points at nodes 3, 9 and 15. See, node 3 is at a distance of 1 meter, that is what we have in the actual one, and node 9 is corresponding to 4 meters, that is the mid length, and then node 15 is at a distance of 7 meters from the left side. Okay. These are at 1 meter, 4 meters and 7 meters from the left side node. Okay. And these are the displacements that we have, and so at the mid length your rotation should be 0 because it is a symmetry point, and that is one indication of whether you got the solution right or wrong. And here if you see a rotation at the 9th node, that is at the mid length, it is 10 to the power of minus 16, which is negligible, that is very, very small value. Okay. Then at the two ends we get a displacement of 0.0032 and it is symmetric, and then the maximum settlement happens at the midpoint because that is affected by the entire loading, whereas away from it the load intensity is smaller, so you have smaller displacement. Then the results in terms of the bending moment and other things. See, the maximum bending moment that we have is 187.7, okay, and then at the below each outer columns your bending moment is 58.89. Okay. That is what we had seen in the classroom lecture. Okay. So we can I will give you these data files and then the program, and you can run. And just to illustrate, what I am going to do is I will just take this case of the truss and the truss example. Just one minute. Well, anyway, I think I do not have the data file, but I will show you the results. See, this is the truss example with the right hand side supported on a boundary spring, and we have seen that sorry, I think this is not the correct one. Yeah, okay, that is. See, this is with a truss with a boundary spring, and I am giving a very small stiffness, like a stiffness for the boundary spring of only 1000, and so if you want to get a compression of 50 millimeters, we need to apply a force of 50 kilonewtons. 50 divided by 1000 is 0.05, okay, and let us see whether we will be able to get it or not, and all the other properties are the same as we had earlier, okay, and let us see. Truss BS. Okay. So, here so our displacements, they are totally different. So, I have actually I wanted a displacement of 0.05, but what we got is minus 0.1366. I think let me just zoom it a little bit. Okay. So, although we applied, we wanted to apply a settlement of 0.05, but we got 0.1366. That is because our boundary spring stiffness value was chosen as 1000, very low compared to the modulus of your other elements, okay, and we can improvise the solution by using a larger value. Okay, let us let's go back and change some property. Okay. Let me just now I am going to change the boundary spring by another 1000 times, okay, and correspondingly we need to apply much larger force, okay, and now I am going to rerun the same data file, and let us see what happens. truss BS. There is something wrong with this. Just 1 minute. I think I made a mistake. Yes, okay. I put a text character, so that's why it is same. Right, where is truss? Okay, now it has run, and see, now you see the result that we have. So, I have given a very large stiffness and then applied a force corresponding to that stiffness, and this node has settled by the desired amount of 0.05 millimeters. That is what previously we got some 0.136, and these displacements are also, they are corresponding to what we had got in the classroom example. Okay, and the settlement is not going to affect our element forces, they are still the same because this is a determinate structure. Okay. So, like this you should be able to use this program GEOFEM for all your classroom problems, and you will get an executable version of this program along with all the data files. I will give you sufficient instructions so that you can run this program, get a result and interpret, so that you will be able to check your answers, because we will not be able to do all the hand calculations, especially for larger problems, and small problems you can do by hand, and when we have very large structure, let us say some 1000 degrees of freedom, obviously you cannot solve by hand, you can use this computer program. And especially as we move into the higher order elements like continuum, we will be dealing with a very large number of degrees of freedom. There you need to use the program, and this particular program has got a reasonably good post processor, but unfortunately that is only for continuum elements. So, when we go into the continuum analysis, I will show you that part of the program. I cannot show much with beam elements and bar elements. Okay. So, okay, thank you very much. So, we will meet in the next class, and this is a brief introduction to this use of GEOFEM finite element program, and I have shown you two examples. One is the truss example and the other is the combined footing analysis. Okay. So, we will meet next time. Thank you very much. Bye.